Okay, 8 a.m. and we can continue. All right, so the main goal of today's class, of course, the Ampere's law. But before we start introducing Ampere's law, we have a few slides from the previous lecture, which we need to discuss. Right? So you remember we started introducing the world of magnetism. We introduced some conventions, some basic ideas which are essential in order to live in the world of magnetism, right? And where we finished introducing Biot-Savart law, right, which allows us to find magnetic field created by a wire, any wire. It can be straight, it can be bent, it can be twisted. Any wire can be. It can be used to find magnetic field created by any wire with current, right? Okay, and we introduced new universal constant mu naught, which is called permeability. All right, and you can think of this constant as a parameter, a constant which describes magnetic properties of vacuum. It's a similar like an idea behind epsilon naught, right? Epsilon naught plays the same role in the world of magnetism, mu naught in the world of electricity, epsilon naught, and mu naught in the world of magnetism, right? Okay, so then so what's next? We need to discuss what about the units, right? What about the units of magnetic field? And now, again, you remember what a month ago I gave a speech about the discrimination between the magnetic field and the electric field, because they equally important, I would say, right? I would say even they are fundamental quantities, electric field and magnetic field, right? But for whatever reasons, electric field doesn't have a special SI unit, but magnetic field does, right? You remember when we introduced electric field, so we just used newtons divided by coulombs, right? So those were units of the electric field. But for the magnetic field, we have Tesla. Special unit, the special SI unit was introduced in order to describe magnetic field. So how come, right? As I said, pure discrimination, right? And my explanation is this. In a week, or maybe a couple of weeks, when we introduce Faraday's law, we will see that magnetic field is involved in production of electricity, electric current. And that is the big deal, right? Lots of engineers, technicians, right? Researchers work there, right? So as a result, magnetic field is used much more often in our everyday life than electric field. As a result, in order to simplify at least somehow life of those people, the special SI unit was introduced so that you wouldn't pronounce this complicated newtons divided by amps times meters. Yeah, it's too complicated, right? So in order to simplify their life at least a little bit, it makes sense to introduce the special unit, Tesla. And of course, Tesla, it's named after Nikola Tesla, great researcher, engineer, not after the car, right? Okay, so Tesla we're going to use. And of course, 1 Tesla, it's a big number, right? I mean, it's a strong magnetic field. It's a very strong magnetic field. It's better to say this way, right? You see, here there's a table of some typical values of the magnetic field, and you see one of the strongest magnets can create only 10 Tesla. Okay, on the face of the Earth, right? Typical lab magnets, right? You see around 1 Tesla. Magnetic field on the face of the Earth is what? 10 times 10 to the power, okay, 5 times 10 to the power of minus 5, right, Tesla. Right, you see 1 Tesla, it's a strong magnetic field. That's why in the previous recitation class, we found a few magnetic fields, and they were on the order of magnetic field on the surface of the Earth, right? Every time we had some constant times 10 to the power negative 5, right? Okay, all right, and so what's then what's next? This Biot-Savart law, which we introduced in the previous class, of course, can be applied to find magnetic field, as I said, created by any wire. Turn bend, twist it, right? Any wire. But of course, the simplest situation, of course, are a straight wire. Infinitely long straight wire with current. So what about magnetic field created by a wire like this, right? Okay, so let's discuss that quickly. So yeah, that's what I said. Okay, so we have a very long straight wire with current. And let's assume, let's say we want to find magnetic field at this point, right? Completely arbitrary point, and it's at the distance d from the center of the wire, right? So how can that be done? You grab Biot-Savart law and integrate it from that infinity to that infinity, because it's an infinitely long straight wire. Right, I did it once when I first time started teaching this course, and students were looking at me with round eyes. So after that, I stopped going through that integration, because it's not that complicated, but still at the same time not that trivial, right? So I usually just say, if you apply this Biot-Savart law for this situation, after like 15 minutes of integration, you will be able to get the expression for the magnetic field at this point. And that expression is mu naught times I divided by 2 pi d, where d, this d, it's the perpendicular distance, or the shortest distance from the wire to the point where you want to know the value of the magnetic field, right? So this perpendicular distance, right? The only thing which I want to say about this formula, usually if you open pretty much most of the books, right, you will see, instead of dr, you will see 2 pi r, right? And you just need to know the meaning of r. It's again the shortest distance. But Knight, the author of this book, for whatever reasons, decided to use d. Usually for me, d, it's a symbol which is used to denote a particular distance, a given distance, right? Not as a variable, right? Just looks so strange for me every time when I see it, right? But again, it's not a crime. It's not a big deal, right? But usually it's a mu naught I divided by 2 pi r, where r, of course, the same meaning, the perpendicular, or the shortest distance. All right, and we started using this formula. Some of you are going to do it in your recitation classes in the afternoon, right? But anyway, so that's how you can find the magnitude. What about the direction? Of course, you can ask. Direction, in order to know the direction, first of all, we need to remember that if you have a straight wire with a current, then magnetic field lines form circles. Something like this. Circles, of course, centered on the wire. Right? You can say why. I can answer, just grab the compass needle and map the field. And you can see that magnetic field lines form circles. And of course, north pole of the compass needle, north pole of the compass needle is going to give you a direction of the magnetic field lines, right? But of course, in everyday life, using compass needle is not very practical. Of course, it's better to come up with some mnemonic rule, right? And we like using right-hand rules. So in this case, we can also come up with a right-hand rule, right? Which can be used to find a directions of magnetic field lines, right? And the rule is that, let's assume that this is direction of the current. Outstretch your thumb in that direction, in the direction of the current, and then curl your fingers around a wire. And your fingers gives you directions of the magnetic field lines. I usually call it a right-hand rule number 2. Right-hand rule number 1 we usually use here in the cross product, right? You see, delta S over R, that's where we use a right-hand rule number 1. I usually call this as right-hand rule number 2. And usually students don't have any troubles applying this rule, right? So, for example, if you apply this rule for this situation, right, you see, current is represented by this cross. Cross means that the current flows into the board, into the screen, right? So right-hand rule number 2, so outstretch your thumb in the direction of the current, like this, right? And then your curled fingers are going to give you direction of the magnetic field lines, and we're getting this direction, right? So what you see on the picture, so it's clockwise direction. Right? So that's how you can find, and of course, direction of the magnetic field. Yeah, these are magnetic field lines, but direction of the magnetic field, of course, every time is tangent to these lines. Tangent to these lines. For example, I can draw a tangent direction over here or there or here, and that direction give us a direction of the magnetic field. Again, these are magnetic field lines, and I'm talking about the magnetic field. Right? Okay, so magnitude, direction. What else do we need? Magnetic field is a vector which has magnitude and direction. Right? Okay. So now let's answer a couple of clicker questions and then move to the new material. Okay, the first one. And of course, the poll is in the chat, right? We have two infinitely long wires with current. Currents are the same. Wires are parallel to each other. but current in the top wire is into the screen, you see, cross, this cross, and bottom wire current is out of the screen because you see the dot, right? So, and as I said, currents are the same, absolute value of the currents. Then we want to find a direction, the direction of the net magnetic field at that point. Okay, you see this point. So what's the direction of the net magnetic field at that point? And you see options A, B, C, D, E, right? Okay, give it a try, and then I will discuss that. A few times in the past, I gave a question like this among multiple choice questions on the exam. Okay, so let me discuss that. So, of course, physics is quite simple. The first wire creates magnetic field which pretty much extends to all infinities, right? The second wire does the same. It creates its own magnetic field, again, which goes to infinity. So, of course, at any point, we have superposition of two magnetic fields. So we just need to look at the superposition of these two fields at that particular point. So let's find magnetic field created by the first wire and the second wire. Okay, in order to get the correct direction of the magnetic fields, right? Let me draw magnetic field lines because, yeah, as I told you several times, of course, they are very, very useful magnetic field lines. And as I told you just now, magnetic field lines around the straight wire with current form circles. Okay, so let me draw a couple of circles here. First, a circle which represents magnetic field line produced by the first wire, the top one. Okay, I need to switch to slides. Okay, right. So, yeah, of course, and apply right-hand rule number 2 in order to find direction of the magnetic field line. Okay, so for the top wire, I use this green magnetic field line. And direction, outstretch your thumb in the direction of the current. Current is into the board, right? And then curl your fingers around the wire. As a result, you see magnetic field line, direction of the magnetic field line clockwise. So that's a magnetic field line produced by the top wire. Now let's do the same with the bottom one. So for the bottom, outstretch your thumb out of the board, out of the screen, right? And your curled fingers are going to give us a direction of the magnetic field line produced by the bottom wire, all right? And again, I picked magnetic field lines which go through a point, the point in question, through this point, right? So that's blue one produced by the bottom wire. And then, of course, what's the direction of the magnetic field relative? No, what's the orientation of the magnetic field relative to the magnetic field lines? it's tangent. So let me draw that green magnetic field produced by the top and blue produced by the bottom. Of course, it must be tangent. So tangent to the green wire, it's a sort of that way, right? So that's a magnetic field produced by the top wire at the point in question. And then in a similar way, I can draw the blue magnetic field. Of course, it will be tangent, so it will be that way, right? Okay, so that's the blue magnetic field. And of course, their strength exactly the same, because that point in question is equidistant from both wires. So this distance and that distance exactly the same, and then currents are also the same. This current and that current, again, the value of the currents are the same. So magnetic field strength must be the same according to the formula which we discussed in the previous slide, mu naught I divided by 2 pi d. Right, so now we have two magnetic fields, of course, with different directions, but the same in absolute value. So now if you add them up, you're going to get pure horizontal direction. Net magnetic field is going to be to the left, right? To the left, right? That's the direction, right? So answer D. Let me check what you pick. Okay, great. You pick D, right? So now let's make the situation slightly more complicated. I turned the top wire by 90 degrees. What will be the direction? The direction of the net magnetic field at the midpoint between these two wires. At the midpoint again. So the top wire again is it is an infinitely long, straight, and current that way. Current, the bottom wire has a current which flows out of the board. You remember, dot means out of the board, right? Okay, try it this time. Okay, it should be enough. Now let me now let me discuss. The idea about discussion will be very similar to the one from the previous slide, right? Just the top wire is turned by 90 degrees. So let me draw again two magnetic field lines. The first one produced by the top wire, the second one produced by the bottom wire. And of course, both of these lines go through the point in question, which is the midpoint, right? Okay, so the top wire, magnetic field line, outstretch your thumb in the direction of the current and curl your fingers. And as a result, magnetic field line will be, if you look from this point, it will be what? Clockwise, right? Clockwise. Right. And at the point in question, at this point, of course, magnetic field, which is tangent, which must be tangent to this line, will be into the screen, right? Then the bottom one, of course, creates also its own magnetic field line, and direction, again, outstretch your thumb, in this case, out of the board, and then curl fingers gives you this direction of the magnetic field lines, right? Magnetic field line. And you see a blue line, which is direction counterclockwise. Okay, so now directions of magnetic fields. The blue one, tangent, right? You see that way, and the purple one, it will be into the board, so cross. So now, in order to make the picture clearer, so let me draw the top view. What are you going to see if you look from the top at both of these magnetic fields, right? So you're going to see something like this, right? So blue that way and purple up, right? So the top view. If you just turn it by 90 degrees, of course, you're going to see what we have here, right? So now, in order to find the direction of the net magnetic field, we need to add them according to the principle of superposition. We need to add them properly because they are vectors, so we need to add them as vectors. So parallelogram method, that will be direction of the net magnetic field. So it's neither of these options, none of the above. It's sort of partially into the board and to the left, right? into the screen and to the left. So that description is complicated, so I picked just an option, none of the above, right? The easiest one. And most of you picked that option, so that's great. Okay, so that's enough about this question. So it looks like you got this, right? So if I give a question like this on the exam, you will most likely you're not going to struggle. So, and now new material. So now it's time to introduce what is called Ampere's law. All right, one of the fundamental equations in physics overall, and of course and also in electricity and magnetism, electromagnetism. It's one of the Maxwell's equations. It's one of the equations in the set of Maxwell's equations. It's better to say it this way. The first equation, which is from the set of Maxwell's equations, we introduced a month ago, Gauss's law. And now it's time to introduce something similar to the Gauss's law, but now we need to introduce it in the world of magnetism, right? So Gauss's law was introduced in the world of electricity, and now something similar we need to introduce in the world of magnetism. And they both have integral form. It means that they're based on some integrals, right? And so since it is fundamental, it means that it cannot be derived. I'm talking about Ampere's law. Right? So it means that we can just present it and discuss it and see how it can be used. Look at applications, right? The same with the Gauss's law. I didn't derive. No one can derive it. Right? All right. So let me introduce it. There it is. So for me, it looks elegant, I would say even beautiful, right? What we have here, we have an integration over here over a line. In the Gauss's law, when we introduce Gauss's law, we integrate it over what? You remember? We integrate it over a closed surface all the time. So we had spheres, cylinders. Now we have integration over a line. It's a line integral. So ds, it's a infinitesimally small section of a line, right? ds, right? Then b, magnetic field. So in the integral, we have a dot product or scalar product of the magnetic field and element of a line, b dot ds. Then you see circle in the middle of the integral. And you remember what does that circle mean? It means integration over something which is closed. In this case, since we integrate over a line, it means in this case we integrate over a closed loop. For example, like a circle. Circle, yeah, it's a closed loop, right? Nice shape. But of course, closed loop can be more complicated shape, right? For example, I can make a closed loop sort of like this, right? So let's say this is my closed loop. All right, and that closed loop we're going to call an Amperian loop. Lots of similarities between the Gauss's law and Ampere's law. And even in terms of in terminology, there we used Gaussian surface. Now we're going to use Amperian loops all the time, right? Then that Amperian loop is again pure imagination. It's your pure imagination. The same like with the Gauss's law. Gaussian surface, it was our pure imagination, right? So we wanted to probe electric field in a certain area, so we would imagine Gaussian surface over there. Now the same thing, right? We can imagine Amperian loop anywhere we want, right? And then any closed loop can be used. It's a universal law. Universal, it means you can apply it at any point of the universe, at any moment of time. And of course for any closed loop. But the key word, that loop must be closed. If a loop is not closed, then it's illegal to use this law. It wouldn't work, right? But anyway, any closed loop can be used. Then on the right hand side of the equation, we have our newly introduced constant mu naught, permeability, right? And you remember when we introduced Biot-Savart law, you remember that ugly constant, mu naught over 4 pi. Yeah, we introduced mu naught in such a way so Ampere's law looks nice. You see, we have mu naught times I, right? But as a result, as a consequence of this, that Ampere's law looks nice, Biot-Savart law looks ugly. You remember the same story we had at the beginning of the semester when we introduced two fundamental laws, Gauss's law and Coulomb's law, right? You remember in terms of epsilon naught, Gauss's law looked nice, elegant, but Coulomb's law looked ugly, right? We had that again, epsilon naught 4 pi, right? 1 over 4 pi epsilon naught. It's a really crazy looking constant. But Gauss's law as a result looked nice, right? So the same story here, right? So then I in, it's a current enclosed or physically embraced by the Amperian loop. Once you pick a closed Amperian loop, right? For example, like this closed Amperian loop. If current goes through that loop, then we're going to count those currents. Right. Okay, so now let's pick a few currents and try to apply this law for this arbitrary situation. Right. Okay, so let's assume that we have a current I1, right, straight wire, current I2 with current down, and I3, for example, still with current going upward. Right, completely arbitrary situation. And in all the examples which we're going to discuss in this semesters, our currents are going to be kind of wires are going to be parallel to each other. Right. So we're not going to have a complicated situation. Okay, so now before you start applying Ampere's law as the first step, you have to pick an Amperian loop. It's the first step, because without that step you wouldn't be able to start integrating, all right? And you wouldn't be able to tell which currents are enclosed. Right? In the Gauss's law we had charge enclosed, now we have current enclosed, right? Lots of similarities. Even the way we're going to handle this law will be very simple. Right? Okay, so as a first step, pick an Amperian loop. Let's say I pick this one. Right? Then, second, we have to pick a direction, because whenever you integrate over a line, you have to integrate in a certain direction. You can move this way integrating or move that way integrating, so you have to pick a direction. And of course, yeah, I should have said that strictly speaking, this integral is far from being trivial, right? It's calculus 3, and most of you did not take calculus 3. But you will see that we are going to take this integral several times, and we are without actually taking it. We're going to use the high school knowledge like we handled Gauss's law. You remember, again, that integral is not simple, is not trivial, but we could handle it just using some knowledge from high school. But of course, every time we justified every steps, right? Every step. Okay, so as I said, you have to pick a direction of your Amperian loop. So let's assume I picked that direction. Right. So then next, let's try to understand the meaning of this integral. Right. Meaning of that integral over the closed loop b dot ds, integration over a line. So let's and again, integration over a line. So when you take this integral, you are all the time on your Amperian loop, right? So you don't go away from the Amperian loop. All the time you are there. Okay, so let's start, for example, integrating from this point. So at that point, there is some net magnetic field. Let's assume it's that way. And you pick small section of this loop ds. So you take a dot product of these two vectors, b dot ds. Dot product is going to give you some number, some small number. Okay, so that's your first number. Then you move to the next small section ds over here, right? ds, and of course there will be some magnetic field at that point b. Again, you take a dot product. You will get the second number, b dot ds. You will add it to the previous number. Then you move to the next small ds, right? Again, there will be some value of the magnetic field. Again, you take the dot product b dot ds, you'll get a new number, and you add that number to the previous two. And you keep moving along this Amperian loop, adding this b dot ds, b dot ds, b dot ds, until you get to this starting point. Once you get there, you have, of course, bunch of b dot ds's. You add them all up. And what's the meaning of that? That's an integral. Integration over a line. If you add all these numbers up, that's the fancy way of showing this. It's an integral over the closed loop b dot ds. That's the meaning of this integral. All right? And again, every time you are on that Amperian loop. Right? So that's the meaning. And of course, the right-hand side, mu naught times I enclosed, where I enclosed is in enclosed current. So now, which currents are enclosed? In this case, it's obvious. I1 and I2. These two currents are enclosed. Current I3 is outside of the Amperian loop, so we are not counting that current. We just completely ignore it. It's outside of this border. Right? Forget about that current. So only I1 and I2. But, of course, now look, current I1 is up. Current I2 is down. So, of course, they cannot go into this Amperian loop with the same sign. Of course, they must go with most likely opposite signs. So how can we decide which current is positive and which current is negative? Right-hand rule number 2, basically. Again, we're going to apply the same right-hand rule, which we just introduced a few slides ago, but in a sort of in the reverse direction. So how it is done? So you pick, here. You not pick, you take your right hand and curl it in the direction of integration. You see, you have a direction of your Amperian loop, right? So curl your fingers along that direction, and outstretched thumb gives you direction for a positive current. So in our particular situation, you see I1 is up, so that current is positive, and I2, which is down, is negative. Again, you curl your fingers in the direction of this loop, in the direction of the Amperian loop, and your outstretched thumb gives you direction for a positive current. In this case, current I1 is positive, I2 is negative. It's again, effectively, it's a right-hand rule number 2, but applied in the reverse direction. Right. So that's how we can make a decision about signs of this current. And one important thing also, where this current I1 or I2 is positioned, it's not that important. For example, I can grab that current I1 and move it, for example, closer to the center, or maybe closer to the, over here to the loop, right? Ampere's law will still look the same, which is nice. Right? Distribution of current, basically, where that current is within the loop doesn't matter, as long as it is within the loop, because if you move it outside of the loop, of course, that story will be completely different. Yeah. Okay, so now in this case, Ampere's law would look like this, right? Integral over a closed loop equals mu naught I1 minus I2. Okay, great. So now, so that's Ampere's law, and of course, the next question, so how, when, and why do we use Ampere's law? Most of the time, we need this Ampere's law in order to find the value of the magnetic field. It's one of the most important questions in electricity and magnetism, finding electric fields and finding magnetic fields. Of course, in this case, magnetic field, right? And here is the trouble, the biggest trouble. Yeah, this law, I can say it looks elegant, beautiful, and so on, right? But at the end of the day, we want to find magnetic field. And where is the magnetic field? It is buried inside of the integral. Inside of the integral. So if you want to find B, you need to somehow extract that magnetic field from the sign of integration. The same trouble we had with Gauss's law. And probably in most of the problems, right, it's extraction of that integral. Mathematically, it's almost next to impossible, right? Of course, you can do it somehow, probably numerically, right? But of course, in this course, we're going to look at situations where there are plenty of symmetries and we can mathematically extract magnetic field from the sign of the integral, and we will be able to find the values of the magnetic field of some nice systems where current is distributed symmetrically, right? Otherwise, yeah, application of this Ampere's law can be quite complicated. But of course, we're going to look at the nice symmetrical cases. Okay, so now after this, let's look at the example. Okay, let me switch to the whiteboard to look at the example. Here's the picture I prepared in advance. We have an infinitely long straight wire with radius r, cylindrical shape, and current is uniformly distributed over the wire. So current I, let's say 5 amps, for example, right? And uniformly distributed over the whole wire. So we need to find magnetic field outside and inside of the wire, right? So let's start with inside. And of course, now we have two ways of finding magnetic field. Right? You can use either Biot-Savart law, right, which I actually refused to apply. I just wrote down that after 15, I said after 15 minutes of integration, we can find that value of the magnetic field at a certain distance from the wire, right? Mu naught I divided by 2 pi d. But now we can derive that actually, that formula actually, right? So first, let's, in part A, let's find, all right, find B outside. Outside. It means that outside R, okay, let me write underneath. R small is larger or equal than R capital. So, and as I said, we have two options. Either you can use a Biot-Savart law, which is not that simple, or Ampere's law. And here, because we have nice symmetrical distribution of currents, application of the Ampere's law will be nice and easy. Okay, reasonably easy, right? Okay, so I wrote down Ampere's law. And what should we do? What should be our first step? Without that step, we would never be able to move any further. First step, you have to pick an Amperian loop. Right. Since we're interested in the magnetic field outside, of course, an Amperian loop must be outside, because basically with that Amperian loop, you probe magnetic field along that Amperian loop. Right. So it must be outside. Then shape. As I told you, 10 minutes ago, you can use any Amperian loop. As long as it is closed, it's good. So you can pick very complicated, right, crazy looking Amperian loop, and you will be correct. But the thing is, yeah, you will be correct, but you will never be able to find the expression for the magnetic field. So what's the point of being correct if you cannot solve the problem? So being correct is not enough sometimes. So in this case, we need to pick the best Amperian loop possible so that you can utilize the symmetry of the problem, right? So we have to be smart. On top of being correct, we have to be smart. So in this case, the best Amperian loop is a circle centered on the wire, concentric circle, all right? And circle is a closed loop. Okay, so let me pick it. All right, so of some arbitrary radius R. So that's my Amperian loop. So first, okay, maybe I will write, no, I will write it here. So that's our Amperian loop of some arbitrary radius r. And of course, r small is larger than r capital. So that's the first step. Now the second step, of course, we need to start taking care of this integral. Okay, let me rewrite it. Integral over the closed loop b dot ds. And steps will be very similar to the steps we used to evaluate Gauss's law, to apply Gauss's law. Right? So first, after this, you remember what we did? We looked at these integrals b and ds on the picture. Right? So let's start with ds. So yeah, I picked an Amperian loop. What I forgot to show after I picked an Amperian loop? Direction, right? We need to show direction of integration. Clockwise or counterclockwise. Which one should we pick? Since we have only one current, one direction of the current out of the board, basically, right? It's better to make that current positive. You remember that right-hand rule number 2, which I just discussed? Of course, yeah, you can pick a direction so that current would be negative. Why? Why would you want to have an additional minus? The answer will be still, at the end of the day, will be the same for both directions. But if you pick sort of not the best direction, then you will have to deal with two additional minuses. Most likely, one of the minuses will be lost by you. So it's better to pick a direction so that the current will be positive. Right? So right-hand rule. So if I go this way, if I pick this direction, which is counterclockwise, then this current will be positive. Right-hand rule number 2, right? Curl your fingers in the direction of the integration this way, right? And then your outstretched thumb gives you direction of a positive current. So in this case, our current is going to be positive, right? So let me pick this direction. So as a result, I can show ds, directions of ds. So this will be my ds. Over here, I can show ds. And of course, maybe at some other points, but 2 is enough. Right. So now I can see direction of ds. Now direction of b. Direction of b, usually I give this justification. Right. Usually books say because of the symmetry, right, it's obvious that direction is tangential and so on and so forth, right? I usually prefer to give this justification. Let me write justification of b direction. Okay, first I will draw, redraw my wire. That's the wire, but just I made it slightly smaller, right? And let's say I want to find direction of the magnetic field at that point, right? So let me draw this auxiliary dash line, which goes through the center of the wire and the point in question, right? And then let me pick a small piece of wire, a small piece of current over here. I can pick it because we have uniform distribution of current everywhere. Of course, I can pick a small current over there. Right? And now forget about the rest of the wire. I want to find direction of the magnetic field created by this small piece of current. So how can I do it? You remember clicker questions, 2 clicker questions which we discussed, 15 minutes ago. That's why I actually like discussing them before this Ampere's law, because now I can use that. Of course, I can draw magnetic field line created by this wire at this point. Of course, it will be something like, right, can I do this? Can I use this? No, it's probably too much. So it will be, okay, let me do it by hand. Something like this. Right. So this is my attempt to draw magnetic field line created by this piece of wire, by this piece of current, right? And of course, magnetic field will be this way. right, tangent to the magnetic field line. Then, of course, I can find also symmetrically positioned piece of current on this side of this line, auxiliary line, which goes through the point in question and the center. And I also can draw magnetic field line produced by this piece of current. Right? So it will be something like this. And direction of the magnetic field will be this way. Right? So now if I add them up, of course, the radial components of this green field and blue field, they cancel each other, and also only tangential only tangential components survive. They will add each other, and you will end up with this direction of the net magnetic field. So as a result, over here, I can draw B, here B as well, and at any other points. For example, a point over here, I can draw B. Right. So now, okay, let me finish this first step and then we'll call it a day. So now I can write, since B is parallel to DS, the angle between them is 0, right? Parallel, 0. As a result, B dot ds equals to the product of two absolute values of B and ds. As a result, the integral turns into this. Dot product disappeared. Vectors disappeared. Now we have only absolute values of these two vectors. You see the first step, very, very similar to the first step which we used discussing Gauss's law, right? And then the second step will be also very similar, where we'll have to use the symmetry of the problem, right? Lots of similarities between Gauss's law and Ampere's law. Okay, sorry for holding you. All right, so next class on Thursday night, where we will finish this example. And more complicated example we're going to discuss in our recitation classes, where there will be a hole in the wire.